Hi everyone. So here we are with chapter 5 and this is day 1. Okay, so this is the day 1 lecture and it is on atomic structure and the periodic table. So with that being said, it will be helpful if you have your periodic table out during the lecture because I will be referring to it. Okay, so let's talk about atoms. So all of the elements on the periodic table are made up of these tiny, tiny, tiny atoms. So for an example, the element lithium is made up of a whole bunch of lithium atoms. Copper is made up of a whole bunch of copper atoms, so on and so on, okay? So now we're going to talk about all of these different scientists, and John Dalton is the first one we're going to talk about. And let's go through these 4 bullet points and see if they are still true today or not. Okay, so the first one, each element is made up of tiny particles called atoms. Yes, okay, that is still true today. The second one, the atoms of a given element are identical. This one right here, we will learn later in this lecture that that is actually not true, okay? All of the atoms, eventually we'll learn, can be a little different, and we'll get to that at the very end. Okay, let's see the next one. Chemical compounds are formed when atoms combine with each other. Yes, that is true. And chemical reactions involve reorganization of the atoms. That is also true. Now, something that I want you to add to your notes that's not on this slide is the name of the model of the atom that John Dalton came up with. It is called the billiard ball model. Okay, billiard like pool table balls, so billiard ball model. So at that time, he discovered that the atom is just kind of like a solid mass, kind of like a pool table ball. And so John Dalton's kind of like one of the first scientists to come up with the model of the atom. But of course, as time goes on and we discover more and more things, we will make changes to this model of the atom. Okay, so J.J. Thompson was the next person to come in and to make a new discovery. So he is famous for his cathode ray tube experiment. And with his cathode ray tube experiment, he discovers the electrons, okay? He discovers electrons. And if you remember any of your chemistry stuff from middle school, electrons have what charge? Negative charge. Good. All right, so let me kind of describe his apparatus that he has here, and I'm going to use one of my really cool laser pointers. Yes, that is right, a lightsaber. All right, so here is a glass tube and is completely sealed. It is vacuum sealed, so therefore there's no air in the tube. He has a positive plate and a negative plate. We refer to that as an electrical field or a magnetic field, and when he hooks that up to an electrical source, he discovers that there are these negatively charged particles coming out of his, what is called the cathode ray tube, okay? And so let's take a look at the next slide, and the next slide kind of proves how he knows that they were negatively charged. Okay, so here we have this particular, so let's use my blue lightsaber this time. All right, so notice how he changes the apparatus slightly. In the middle here, he adds an electrical field, okay, in the middle of it. So he has a positive plate here and he has a negative plate there. Notice that these particles are coming from the negative side of the plate over here. And look how they bend up towards the positive plate, okay? So opposites attract. Particles from the negative side bending up towards the positive plate. So that is how he confirmed that these particles are indeed negatively charged, and we call these the electrons. So now that we have electrons in our model of the atom, we are going to throw them in here. So that's what all of these little things are. So let me use, look, I also have a green lightsaber. Look at that. Okay, so let's see. These little pink, red looking dots, those are electrons, okay? Those are supposed to represent the electrons. And so you kind of still have your positively kind of like solid mass, and then now electrons are just scattered throughout. And the reason why they call this plum pudding, okay, they call this the plum pudding model. I know that we're not too familiar with plum pudding, but I believe that plum pudding is an English dessert, and plums are like raisins. So it's kind of like pudding, and then raisins, or plums, so to say, are just kind of scattered throughout, okay? And those plums represent the electrons. Now that the electrons have been discovered, Milliken is famous for his oil drop experiment. So we know that the electrons are negatively charged, and so Milliken did more studies on the electron to discover the actual magnitude of this negative charge. So let's take a look at his apparatus here. So let me see. I'll use green. Okay. So let's see. So he has this box. Okay, look, positive plate, negative plate. So we have another electrical field here. So what he does, okay, here's some oil. He's squirting some oil into this box, and they fall through this hole here, and they and what happens, these oil drops are like suspended in air between these two plates. And X-rays, says X-rays produce charges on the oil drops. So X-rays, yes, are being shot through this box, okay? And through this whole apparatus, he's able to determine the actual magnitude of the charge on the electron, okay? So yes, we know it's negative, but he figured out like how many coulombs that the electron actually produces. Okay, now the next person to come in is Rutherford, Ernest Rutherford. He is very famous for this gold foil experiment. So let me explain what this setup looks like. All right, so let's see. Right there is the piece of gold, okay? And over here in this box are alpha particles, all right? That's what that symbol right there is, the Greek letter alpha. When it's typed like that, I know you guys think that that is a letter A. It is not a letter A. This is how you write alpha. It's kind of like a fish, all right? That's alpha. Alpha particles, they are radioactive, so that's in a lead box. They do have a positive charge, okay? They do have a positive charge. So what he did was let's go this way. He shot this piece of gold foil. He bombarded the piece of gold foil with a whole bunch of these alpha particles, okay? So some of the particles you can see actually pass straight through, but some of them, like in this region here, were actually deflected back, okay? So with this whole gold foil experiment, he's trying to prove whether or not Thompson's theory is correct or not. So if Thompson's theory was correct, then all of the particles would have passed straight through. But as we can see, that they did not pass straight through, okay? Look at those that were deflected back. So that's indicating to us that the atom must contain a very small dense center. And what do you think we call this very small dense center? Okay, so think back to middle school. Inside the atom, we have a very small dense center, which we call the nucleus. That is correct, okay? And so if the alpha particles have a positive charge, and what do you know about charges? So if these particles here are being deflected back, then that means that most likely not only do we have a very small dense center, but we know that it's also most likely going to be positively charged because like charges repel. So now we have a comparison between the results of Rutherford's experiment, if Thompson's theory was correct, and then what actually happened. So let's take a look here. Okay, so if Thompson's theory was correct, see how all these alpha particles, they would have passed straight through, okay, if Thompson's theory was correct. But according to the gold foil experiment, this is actually what happened, okay? Most of them, yes, they do pass straight through, indicating that the atom is made up of mostly empty space. But a small percentage of them were deflected back, indicating that we have a very small dense center, which we call the nucleus, and it has a positive charge. So basically, with the gold foil experiment, Rutherford discovers the nucleus. So now we add the nucleus into our structure of the atom. So now we can put everything together. So the subatomic particles that you guys are very familiar with, protons, electrons, and neutrons. So you need to be familiar with those. What is the charge on protons? Positive. What is the charge on electrons? Negative. What is the charge on neutrons? No charge, neutral. Okay, so no charge, neutral. So the nucleus, that's where you're going to find the protons and the neutrons, in the nucleus. Therefore, the electrons are on the outside of the nucleus. Okay, so basically, here's our nucleus. Okay, so if this is our structure of the atom, there's our nucleus in the middle with a positive charge, and then the electrons are just on the outside surrounding it. All right? So now we're going to talk more about the periodic table. So it will be helpful if you get your periodic table out, so you should do that now if you didn't do that at the beginning. And we're going to go over some terms. So the first term we're going to talk about is atomic number. So the atomic number tells you the number of protons. Okay, the number of protons. So now let's take a look at the periodic table so you can see where that is located. All right, so here's my periodic table. So that is located here in the upper left-hand corner. Okay, so that's that number here that goes in order. 1, 2, 3, 4, and I'll keep going. 5, so on, so on, so on. Okay, so that number tells us the number of protons, and that's how we identify what the element is. Okay, so for example, the element beryllium, it's number 4. It will always have 4 protons. Okay, it will always have 4 protons. And so the periodic table is arranged in order of increasing atomic number, not atomic mass. Okay, it's arranged in terms of the atomic number, not the atomic mass. The other thing you need to know, the element symbols, which once again are the letters, so you are familiar with that. So that's review. You already know what groups are. Groups are the columns. We also refer to the groups as families, okay, as families. So as you go down the group or the column, they are in the same family because they have similar chemical and physical properties. Just like people in the same family may look similar or they may behave similar. The rows are what we call the periods, okay, the periods. So some people like to remember it as, well, I write horizontally and I end with a period, okay? So the rows are the periods. Your atoms are going to be neutral. There's no charge on your atoms. So since the atomic number, okay, tells us the number of protons, that will also tell us the number of electrons. So remember, protons are positive, electrons are negative. So since the atom is neutral, therefore positive and negative charges will be the same. Okay? Now we're going to go over this term isotopes. This is really, really important, this term here. Isotopes. So if you remember at the very beginning, we talked about Dalton and how one of the bullet points was not true. How we later discovered that the atoms are not necessarily identical. They can actually be different. And this is where isotopes come into play. So isotopes, number of protons remains the same. So that means that that proton number, which is the atomic number, never changes for that particular element. But the number of neutrons vary. So since the neutrons vary, therefore we get a different mass, okay? And that's where we get this term mass number. So you need to know how to calculate mass number. Mass number, protons plus neutrons, okay, will give us the mass of the atom. Mass number is just a whole number that we're going to get, okay? It's a whole number. Where are your protons and neutrons found again? Where in the atom are they found? In the nucleus. Okay, so basically, whatever's in the nucleus makes up the majority of the mass of the atom. Now, the electrons, we're not saying that the electrons don't have mass. They do, but their mass is considered to be so insignificant that we don't even count it. Okay, so protons and neutrons, once again, are found in the nucleus. You add those two things up together and we get the mass. All right, let me expand, though, and talk more about isotopes. Okay, isotopes. So once again, an isotope, the number of protons remains the same, but the neutrons vary. So we're going to take a look at this example, talking about 3 isotopes of hydrogen. So find hydrogen on the periodic table. It should be pretty easy because it is the first element. What is the atomic number for hydrogen? Okay, it is number 1, right? So that's telling us that it has, so I'm going to write proton equals 1. Proton equals 1. Proton equals 1. So these are your 3 different isotopes for hydrogen. So they all have 1 proton, and then it tells us right here how many neutrons there are. So we know that protons plus neutrons gives us the mass. So therefore, 1 plus 0 equals 1. Okay, that's why it gets the prefix pro. So if we take a look at the next one here, so this is deuterium. So 1 plus 1 equals 2, and that's where it gets the prefix "du", because that means 2. Now we look at the third isotope, 2 neutrons plus 1 proton gives us a mass of 3. That's why it's called tritium. Okay, so that is an example of an isotope. Once again, notice here, protons remain the same. The proton number for hydrogen is always going to be 1, okay, because it is number 1. So protons always remain the same, but look what varied. The neutrons varied. Therefore, we got different masses for each one. So here's just a picture emphasizing once again what isotopes are. So this is sodium, okay, so you can find sodium on your periodic table. It is number 11, all right? So let's take a look at this first picture here. This is the nucleus, and it's just expanded, all right? So it has 11 protons and 12 neutrons, okay? So notice that sodium is number 11, so look how the proton number is always number 11. Even in this one over here, proton number is still going to be 11 because it's number 11. So, and also I'll just point out 11 electrons in each one because the atom is neutral. But look what's different. This one has 12 neutrons, this one has 13 neutrons. That's why the masses are different, okay? So don't forget, when you add those, so that's 23 over here, and that's 24 on that side. So that's where that top number comes from. That's what that represents. That represents the mass, okay? So once again, protons are the same, 11, 11. Neutrons vary, 12 and 13. Therefore, we get different masses, okay? Those are isotopes. So this is the last thing we're going to go over for this lecture. It is just the representation of what the element symbol might look like and what those numbers mean. So I know this is written correctly on your notes. This X here, once again, it downloads weird in this program. Okay, there we go. X is there. So this number up here, yes, that tells us the mass number. That is also referred to as a superscript. When it's up high like that, superscript. Okay, that's called a superscript. When the number is down low, that's that one, okay, that tells us the atomic number, and that is called a subscript. Okay, subscript. Script, how do I spell script? Okay, subscript, all right? So the atomic number, which is the number of protons, that is the number that goes in order on your periodic table.